Yeah, that's right. That's great. Okay, guys, good morning. So last week uh, we stopped at our last lecture. We stopped here at the rectifier, and then we talk about how this gives you like half of the wave if you don't have a capacitor, and if you have a capacitor, you can see that the voltage actually charges to this peak if you don't have a resistant load connected. But if you do have a resistant load connected, the voltage is going to drop a little bit because energy comes out from capacitor to supply power to the resistor. And we said, depending on the size of capacitor, if the size of capacitor is very big and the line drop is kind of a little flat, but if the capacitor is very small and the resistor also like small ohms, and then it might actually drop quite dramatically. It might actually drop to zero before the next cycle starts. So one of the questions to ask is that, okay, so if I want relatively flat output waveform, I mean, it's not possible to get actually flat because there's always some voltage drop when it passes the peak, right? So if I want kind of a relative flat output voltage at the resistance, what do I do? Well, you need to select a larger capacitor for sure. And how large is large, right? So what you can do here is we can kind of doing a few I don't know why this doesn't go away. No, that doesn't go away. Okay. So what we can do is we can assume in this mathematical calculation, it can also be done for the full wave rectifier and a half wave rectifier. The process is almost same. So what we're going to do is we assume we owe. Now you might say, okay, it is not constant. It actually drops one peak a little bit down, but let's assume it's constant. Or at least we can assume there is average at the output, right? So there's maximum, there's minimum, but overall, there's going to be some sort of average, yeah, because we owe. Now think about the process when the try here. So this is the process. We're doing this halfway right now. Think about the voltage reached maximum and it actually drops to some point later. And what we want to find out is how much is the voltage drop between the peak and the maximum and between the peak and the minimum of the output voltage. So that is process. Now thinking that between these two peaks, you got the period of the waveform is t. So from one peak to another peak. If you do a full wave rectifier, it's going to be half t because you get one half sine wave, another half sine wave flipped. So if we look at it from this peak to the next peak, the total time is t. During this time, of course, it's not exactly to the peak. It's actually coming to this point. Okay, so this is time. Let's call it delta t. So during that delta t, where is the power coming from for the resistor? So it's coming from the capacitor. So the capacitor actually supplies a current to the resistor. Now, because the current supply current to the resistor, so its voltage actually drops. Now, for the time being, we can actually do a mathematical equation to solve this because for this circuit, you look at circuit again on the left hand. When this in the negative half cycle, the diode is off, which means what you have is just a capacitor connected to a resistor. Okay. So this is a very simple loop circuit. You have two components. So ideally, you can simply write the relations between the voltage. So you can say VC equal to R times let's go IC, okay? It's the same current, whether it's called IL or IC or IR, it's the same thing. It's the same loop, right? So in this case, what is the relation between voltage and current inside the capacitor or across the capacitor? It's IC equal to C dVc over dt. So now we can plug in the second equation to the first equation. What we got is Vc equal to RC So this is a very simple first order differential equation. And it's easy, you guys can solve this. If you don't remember, because always look back your mathematics 150 and you'll find out how to solve this problem. It's very simple, right? You got like e to the something, omega t, e to the t over tau. But here we don't want to go through process. We just want to give you guys a kind of an easy way to get this out. So what we're saying, because what we're doing is we assume this VC is linearly changing. So what we're going to get is delta VC is change over delta T. So assume that this change in the process is kind of linear. It's actually not linear, by the way, but of course, assume, you can see that if you actually do the simulation or do the mathematical calculation, you'll find that this error is not that big, especially when C is big, okay? So when you do this, you find out, okay, so VC is RC delta C over delta T, so I can find out with delta C equal to VC over delta T times divided by 1 over RC. And because this is delta T, if you look on the right hand of the screen that where I have the picture, that delta T is actually, if the C is big enough, that delta T is approaching that period of T. So plugging back that T over back over here, we get delta T is VC over T times 1 over RC. So this is delta VC, or delta VO, or delta whatever you call it. I mean, it's the same voltage across the capacitor. So the next question is that, okay, if I want my ripple to be small, I need to design the capacitor so that I get my ripple within range. So let's say you have, let's take some example. Let's say your VO is, let's say your VO, or in this case VC, square root of 2 times 110. So it's roughly 141, 150 something. 1.14, right? 1.41. So let's say 1.55 watts. Anyway, and our T is equal to 1 over F is 1 over 60. That gives you roughly, say, 17 milliseconds, I guess. Again, those numbers are rough, okay? You guys can use calculator to get an exact value. But if you have a load resistance, let's say to have, say, 1 kilo ohms for a typical electronics load, 1 kilo ohm. So now you can plug in all these numbers back to get your C. So your C is going to be delta VC times T over VC. Delta VC over VC times T times C times T times R. So that gives you your requirement of C. So let's say I want the ripple to be within, so this is given typically is the ripple is delta VC over VC equal to say 5%. So that is a kind of, okay, 100 volts, 5%, 5 volts. So I want the ripple to be within, say, a few volts, 5%. So you plug in this back, you can get C equal to 0.05 times 16 milliseconds times R, which is 1K. And the K and then the milliseconds cancel. So you got this to be 0.8 farads. That's quite a big capacitor. So you can see that here, even though it is possible to design a large capacitor so that you can have little voltage change, but the capacitor is actually fairly big. Yeah.
So if I wanted delta VC to be like, we wanted a straight line, it'd have to be infinite.
Right. I mean, you can simply look at this equation. If you want this to be zero, to be like a 0, right? No, did we get it wrong?
Did we flip VC over delta VC?
Oh yeah, we flipped. Okay, sorry, this was wrong. I'm sorry about that.
Okay.
No, this was not good. Yeah, no, we got the equation wrong. So actually, C is at the bottom, so we need to multiply C on both sides. So C equal to VC over delta VC, what? Delta VC equal to VC equal to RC times delta VC. So C equal to VC over delta VC. I was wrong. Divide by R times T. Okay. So so this equation, right? So you're right. If delta VC is 0, I mean your C will be infinity. The smaller the delta VC, the larger the C that you need. So that's for the half wave. But for full wave, we reduce the T by half. So it's going to be like replace this T by 1/2 T, then you'll get yeah, so that's correct, because when you have double wave and this becomes half T, so the C is reduced by half. Okay, so for the same ripple. Okay, so this is in the book, there's a section talk about this. You guys can go through a little bit more detail.
Isn't that T supposed to be at the bottom of the fraction?
T is at the bottom. No?
Well, to get a C, we multiply both sides by C and divide by C.
So this T is here, right? T third.
Multiply both sides by C, and C should be at the bottom of the fraction.
C, let's see.
Multiply both sides by C and divide by VT.
So T is at bottom.
Yeah.
Oh, okay, yeah, you're right. No?
Over RT.
Let's see. So let's start over. So VC equal to RC, third VC.
Too much math in it.
Sorry about that. ICC dV over dt. So RC delta C over delta T. Okay, so we'll find C, which is delta VC over T. Yeah, that's over T. Okay, VC. Okay, times R. So that's C divided by R. So C. Okay. Now I think we did something wrong here. Let's redo it. Let's take this equation here. So we said VC equal to RC delta VC over T, right? That's the equation that we found from here.
I think your current or capacitance equation.
Current of a capacitor is C dVC over dt. That is correct. That is correct. So we want to find a C. From this equation here, we get C, just move on this side. So VC times T over VC delta VC, and then divide by R. That's correct. So it should be divide by R. So yeah, this equation is correct. So we just, maybe here it's not clear.
That'd be T over R would be like.
It should be R, yeah. So the larger the R, So apparently you need less C, the smaller the T, you need less C, so that is correct now. Yeah. So this equation is correct. Sorry about the previous mistakes. So if you do the full wave, apparently nothing changes except that the time interval becomes half cycle instead of a whole cycle. So then apparently you can reduce it by half by doing this. I mean, this apparently this assumption is not it's just again a reasonable assumption because if you look at the blue curve, it drops before it reaches the next peak, right? So there is a difference between the actual time interval and the half period in this diagram. So your calculated C will actually be slightly, slightly less than what you need. Okay, so now we're going to jump into just a few very unique applications of diodes. These are very interesting circuits. I mean, think about it. You can use a diode to do something you might be like never imagine. In this example, we have what we call a super diode. A super diode is connected to op-amp. Okay, so we're going to analyze a little bit of what's going on with op-amp. Suppose Vi equal to suppose Vi is positive, and we can find out what the voltage is at the output. So based on the op-amp theory, you guys remember, and that's something we're going to test you guys next week. The voltage at the two input terminals are supposed to be the same, which means the voltage at here is going to be positive, and here is going to be, let's say positive, I will just give you some value, 5 volts. So at the negative terminal, it's going to be 5 volts. And at the bottom, you see of the diode, it should be 5 volts because that's just a wire. So your VO is equal to 5 volts. And in this case, I want to ask you guys, how much is VA? VA is on top of the diode. And VO is at the bottom of the diode. So the diode voltage is 5 volts. Now, maybe a little bit further, I give you R is 1K, and then let you guys to figure out. So cos IO through R. So how much is IO then? This you guys can calculate, right? So it's 5 volts divided by, that gives you 5 milliamps, correct? Okay. So now tell me, how much is VA? Well, I guess it would depend on which kind of diode you're talking about. Is it ideal diode, it's a constant voltage diode, or is it like a spice model diode, right? So really, now let's assume that this is a constant voltage drop diode, just the piecewise linear model, 0.7 volts. And how much would be VA?
It would be 5.7. Yeah, 5.7.
5.7, okay. So VA is 5.7. So, which is correct. But the question is that, how do you get that? I mean, why do you know it's 5%? Why is it not like something else?
You know that the current, the I0 has to come from somewhere.
Right.
So we're assuming that this is an ideal op-amp, so there's no current coming from our minus side.
The
current has to be coming.
You're absolutely right.
The diode.
The current, that's why I want to tell you the IO, because there's a current flowing through the resistance RO, and that current has to come from somewhere. And the input terminal, 5 volts there, does not provide you with any current. So the current has to come from the op-amp, the output terminal. So therefore, this diode is what we call forward biased or on or conducting. Those are the same thing. So the diode is conducting. When the diode is conducting, it's a constant voltage drop model. So we're using, therefore, it's 0.7 volts across the diode. So you 0.7 plus that 5, it gives you 5.7 volts.
What happens when we input a negative voltage.
Exactly. That's the next thing that we're going to discuss, right? So the next time we're going to say, okay, Vi is negative. So if Vi is negative, I'm going to redraw the figure, just make sure that we don't mess up the figure. So the next figure we're going to draw is the input is negative. Let's do something similar. 5 volts. Okay. So based on the op-amp, ideal op-amp property, if the input terminal is 5 volts at the positive terminal, and the negative terminal would have minus 5 volts. So you might say, okay, well, that's good. So how much do we owe then? So VO is going to be negative 5 volts. So if VO is negative 5 volts, how much is IO? That's also negative 5 milliamps, but it's going up, right? It's negative because, right, it's going up. So now, do you guys see a problem? Well, you got this current going up 5 milliamps. The diode will prevent it flow back, and this thing does not conduct any current. So apparently, that's impossible. So that is wrong. So this is not possible. So not possible means you cannot current flowing upwards. So which means that the current is going to be then, let's see. So then your current has to be 0. You cannot flow current. If you current flow 0, how much do we owe then? 0. So if we owe is 0, and then how much do we owe?
Negative 4.3, or it would just be 0.7. VA would be, or no. Yeah.
Well, okay, so the gain, if this is an ideal op-amp, the gain is infinite. So we have V0, so the voltage across the thing is not 0 anymore. So our voltage across it is negative 5 volts. So it's negative infinite. So there is.
Yeah, you guys are very smart. Exactly, because the way that if what we can do is we're gonna add one more thing. Let's call V minus. Okay, so if VO is 0, V minus and VO is connected on the one line. So V minus is going to be 0, right? So if V minus 0, you might say, is this violating the rule that op-amp has to have this two terminals have the same voltage? Well, it depends, because if you have current, everything flows smoothly, yes. But now we're blocking, there's no current flowing. If there's no current flowing, actually, they can be different. So V minus and V plus can be way different. So V plus 5 volts. So now you have a minus 5 volts, yeah. So now your V plus and minus V minus is going to be minus 5. And you multiply by the gain is infinity, that gives you your right. I mean, for real op-amp, it will now go to negative infinity, but it go to the saturation, which means how much voltage. If this voltage is 10 volts, so this voltage is negative 10 volts, so it's going to go to, so VA is going to go to negative 10 volts. And the output property we plug it here is that if Vi is negative, output VO is 0. If VO is Vi is positive, output is same as the input. So so this is a very interesting phenomenon. Is that okay? You get all the output. So then you might say, okay, why would you call it a super diode? Well, there are two properties. One is that when voltage is negative, right? It's blocking, so it's a diode like reverse blocking. If voltage is positive, your output is actually 5 volts. There's no voltage drop from the input. No voltage drop in the input, right? So 5 volts. So this is always 5, whatever, 4 volts, 1 volt, 1 volt, or even 0.5 volt, 0.5 volt, whatever, you know, that is going to be some voltage over there. So that is like super diode. No voltage drop on the diode. Your output always same as the input. And all the current that going through the load resistance is coming from the op-amp, not coming from the diode. So diode actually, I mean, it is coming from diode, but it's supplied by the op-amp, not from the input. So if your input has a large internal resistance, in this case, actually works perfect. You know, and we can probably draw a circuit here, just give you a little bit of, I'm going to draw on this corner here. So let's say you have a diode circuit. So this is a very clear picture of what's going to happen. You have a sensor that comes with a certain voltage, and you got a 10K internal resistance, and you got a diodes you want to rectify, and you got load that is 1K. So when it's positive, what happens? Yes, the voltage is going to cross the diode and then supply both resistance. So if your input is 5 volts, how much voltage do you get at the output? Like 0.45 volts. Not 5 volts. It's very small. It's like less than 10%. Okay. So you get a significant voltage is dropped inside the internal resistance. But if you have this one, you have the other circuit, right? So let's draw the same circuit, but this ugly diode. Okay, so I guess I can use current as example. So in the top case, how much current you get is VI minus 0.7 divided by 11K. For the bottom one, how much current you get? Is basically VI divided by 1K. So this is VI. The reason is VI because there's no current. You know, again, you guys look at this. There's no current into the terminal. So what our voltage over at the input is actually connected at the gate, right? So if this is VI and this VI and this VI, so VI over 1K gives you the load resistance. But on the top one, you have first minus 0.7, and second you have divided by the total resistance of the loop. So that's why you get much smaller. So if VI is like 5 volts, I mean, here you got only like 4 milliamp, 0.4 milliamp, but here you got 5 milliamps. It's 10 times different, more than 10 times difference. It help you get much larger load current. Yeah, like if you want to drive your speaker, well, you want more current to be louder, right? So this way, why we do this as a super diode, okay? Okay, so next up, we're going to talk about another circuit called DC restorer. This name is interesting. Huh? Book. The input is AC, which is not sinusoidal, but it's still AC. It's a square wave. Why we call it AC? Because sometimes positive, 4 volts, sometimes negative 6 volts, and it's a periodic waveform. It doesn't have to be periodic, but in this case, we do have a periodic form, and it's an AC. Okay, guys, this is AC. Sometimes people say, "Oh, this is not AC. This is a square wave." Yeah, square wave is AC. But of course, it depending on where the middle is. I mean, if square wave everything is above 0, that's not AC. Okay, but a sine wave is a sinusoidal AC.
AC is negative.
AC means sometimes positive, sometimes negative. It's AC. Alternative between positive and negative, that's AC. Regardless, it's square wave, sine wave, triangle wave, sawtooth wave, whatever. So it's AC, okay? So this is AC. But Sometimes in some applications, we don't want that AC. We want that to be all positive. So all positive, how do you do that? Well, one way you can do like a filtering. Yeah, so that's one way. Well, filtering is kind of complex circuit. For filtering, like you have low pass, you pass the DC, but you get the AC things filtered. So in this case, we simply do a very simple circuit. We connect a capacitor and a diode, and we'll be able to get to move the AC into everything positive. So that's why it's called a DC restore. So we remove the AC, we like restore the DC. So how does it work? Well, let's look at the middle circuit. Let's look at middle circuit. So when VI is positive, you know what's going to happen? Well, the thing that VI is positive, let's say initially we see 0. We see 0. If VI is positive, you got a diode blocking any current to go through. So even though VI is positive, your C is going to be like 0. Nothing really happens here. And all the voltage actually across at the output is going to be yeah. Okay, let's actually, you know what? It's actually good to start with negative. I think it's better because let's start with negative. Because that way we'll understand a little better why VI is less than 0. So if VI is less than 0, which means we have current going like about, we have, so diode D is on, and current is flowing from source through diode to capacitor. So eventually we can find out how much VC. Give it more time. Like suppose the C is, suppose that enough time. Of course, there's a period, but suppose that's enough time. So what happens to VC? And that's also suppose that VD is 0. Suppose it's an ideal diode. Okay. And then how much do we owe them?
VO would be 0.
VO will be 0. Okay, good. Yeah, VO will be 0 because it's conducting current is on. Okay, so how much do we see as mark? VC will be same as VI. Yeah, because all the voltage across the diode and applied on the capacitor. You see the loop. Okay, so we see same as the mark. If you mark the VC, the other direction will be different. So we see actually this way is VI. Huh? Not yet. We're gonna go there now. So VC is VI. Let's assume is 5 volts. This is actually 4 volts. So in this case,
But it's -6.
huh?
Yeah, it'd be -6.
-6 volts, right? You're right. Good. -6 volts, but it's going to be actually 6 volts.
Yeah, because we're cross.
Focus currents in the opposite direction.
-6 volts. Well, currently going this direction. So here. So here is positive. So negative here means positive here. Positive here. Yeah, so it's 6 volts, right? So, and then what we're going to do is now we're going to go VI is larger than 0. So if VI is larger than 0,
So we're gonna have an instantaneous change.
yeah, instantaneous change, right?
But the capacitor is going to resist the instantaneous change.
The capacitor doesn't change. So capacitor initially voltage is going to be 6 volts, right? So that doesn't change.
Well, it should be -6 volts. That's how you get the full differential of 10.
Negative, let me see. So this is a negative means positive here, negative here. Oh, you're right. It's a negative 6 volts. Positive at the bottom, going this way. No, actually, it is 6 volts. Okay, so let's move on. So if we see 6 volts and now no current. So here I'm going to redraw the circuit. So here to here is 6 volts. So now no current. So now we imagine VO. So VO is equal to, yeah, VI plus VC, because you see those 2 voltage sources are kind of in series, right? There's no current. So it's going to be 4 plus 6, it gives you 10 volts. So what we're saying that if the capacitor is size is right, and because there's no resistor in the circuit, so but ideally, I mean, the voltage on the C won't change instantaneously, but it's okay. You know, for this example, we're just assuming that this voltage would actually change on the capacitor to 6 volts initially, but it would take some time, you know, because the diode is actually having some internal resistance, right? You remember the spice model, right? So the initially what happens is that in the initial cycle, the voltage is not going to go like this. It's probably going to go something like this. Okay, but then you'll move on to another moving on, and then but afterwards, you know, it's going to go like a square waveform. So this very useful circuit we call DC restore, because we actually remove all the AC and we shift everything up. There's no negative anymore. Everything is positive. You can certainly do the same without a diode. You can do like a filtering. You guys remember if we do like a low pass filter? How do you guys remember how low pass filter? Have you got no idea?
A low pass filter.
Yeah.
Is if we want to do with an RLC.
Yeah, RL. Just say RL. Oh, no, RC.
RC.
Yeah.
So we would just do a resistor and then a capacitor, and then our voltage out is parallel to the capacitor.
Which one? So it's capacity here?
Yeah, well, our voltage out would be parallel to our capacitor. That is a high pass.
That's a high pass, right? So okay, so the reason you identify high pass or low pass, you look at the impedance of the capacitor. The impedance of capacitor is omega C, which one omega. So when omega approach infinity, 1 over omega C approach 0. So therefore at high frequency, the top circuit over here, omega C is 0. So all the voltage applied at VO, so that's a high pass. At the bottom, when omega C zeros, at high frequency, the output is 0, but at low frequency, it's open circuit. So this is low pass. So and of course you connect your load over here. You see, with this type of circuit, what happens is that, yes, you can filter some of the components you don't want, but the problem is that you cannot do 100%. So it's always going to keep something there depending on the cutoff frequency, you know. But the issue, of course, this one is that once we add a load resistance at the output, things are going to change, because that's going to have current flowing from a capacitor to the resistance, and So
This, assuming that we don't go over breakdown, there will be a little bit of loss due to the voltage.
So what I'm saying is, yeah, so what I'm saying here, if you got a resistor connected, now you're having trouble because not only the current goes this way once it's active, the current also goes this way, right? So once you're positive, it not only goes this way, but also goes this way. So you lose a lot actually, not just a little bit. I mean, it's not, it's no longer DC restorer because the voltage always across the resistance is always negative 6 volts. Yeah.
Solve that by adding another diode in series with the load resistor.
I guess, well, depending on what you need, right? If you want to get some current to supply your load, that's not going to work. So to solve this problem, you can combine this one with our super diode. Right, so this is how it exactly works. Okay, now you got restore DC, a super diode. Now you got everything right what you need. So yeah, so it's very interesting. Anyway, so this is another circuit which is very similar to previous one. But what we're doing is we are boosting the AC up a little bit instead of see this voltage coming in. It's a perfect sinusoidal AC, positive, negative over time. And then we want an output that is shifted up, not only just positive, but actually more than positive. So the bottom of the AC sine waveform does not actually touch 0. The easiest way to do, is to simply add a capacitor. I mean, add a capacitor, C, and also a voltage, the DC voltage source. So if you don't have, like from the previous slide, if you don't have this voltage, what do you get?
Know that the negative part is.
Yeah, so it's going to be shift everything up, right? But when you add a voltage, see what happens? Well, you imagine at the output that VO is not longer just going to be VI, but actually it's going to be plus VCC. So this VO is going to be VI plus, so it's VI plus plus 1/2 VP, or they call it 2 VP. So actually plus VP plus VCC. So everything is shifted up. So the bottom VCC and half is VP. But the bottom figure is simply VI plus VP. So half is VP, so half is VP. Well, this is very, I don't, it doesn't need much more explanation. It just does it that way, okay. And then there's another circuit called the voltage doubler. By the name, you already know what this does. It doubles the input. The input is 1, it gives you 2. If your input is 4, it gives you 8. It doubles your input. How do you double the input? It's a combination of this capacitor and diodes. If you look at okay, so look at the left hand, C1, D1. Is this going to assemble the circuit we said the DC restorer? Yeah, flip back your slide to see that circuit. Is that same?
Yeah.
No, the diode is flipped, right? So actually, what this does is that D1 is going to do the positive half cycle. So if voltage is positive, you get current through the left loop. So if VI is positive, C1, D1 conduct. If C1 and D1 conduct, suppose VD1 is 0, because it's again, we're going to assume this ideal case just to make it easier. So VD1 is 0. Now how much is VP?
VP is
Okay, VC1 in fact. We call it VC1. VC1,
all
it's going to follow the AC voltage, it's going to charge up and all the way to the peak. So it's going to be same as VI. Actually, it's going to charge to its peak of VP. Eventually, it's going to charge to its peak, to VP. So that's one VI is positive. Is there current in ID2? Well, at this point, I say no, we don't know, but let's assume there's no current at this point. So now we're going to move over to VI is negative. So VI is negative. Apparently, you cannot have current in the first loop anymore, right? Because the diode is going to prevent the current flow. So what we're doing is you're going to have current flowing this way. So you're going to have current flowing. So you have D2 conduct, and you have VC2. So probably what I'm going to do, because the middle diode does not connect anyways, I'm going to just remove that. Okay, so make it easier, right? I mean the middle one, the middle D1. The D1 is reverse bias, no current, so I just take it out. Just easy for you guys to look at the loop. You don't have to take it out, I mean, I join, but just for easier to analyze. So now look at this circuit. This is one loop. And again, assume VD2 is 0, ideal diode. How much is the voltage at VC2?
two capacitance.
So VC2 now is going to be if you look at, okay, so if you look at the which is next, you do loop analysis. So this is one voltage, this is another voltage, positive over here, right? So positive over here. So this one, let's say it goes to VP. So this one VP, another VP. So therefore, this is going to be 2 VP. So that goes to 2 VP.
There's one VP from the capacitor from last.
Yeah, well, there was 1 VP from the last capacitor charging up. Actually, it's going to be should be minus 2 VP, right? Plus, yeah, because really it has to, yeah, so it should be minus 2 VP. So let me. So it goes actually to minus 2 VP. And that's in the negative half cycle. Actually, this is correct. Why is this marked here? VO as 2 VP. Actually, if you look at this curve, it's correct. It shifts everything down to from 0 to minus 2 VP. That's the output.
Because it's by changing the direction of our initial diode,
Oh, okay.
it's doing the negative of what we were doing.
Oh, okay. Yeah. Okay. So this one, we shift everything down, but we actually doubled the output. So that's called voltage double up. Of course, the output is actually negative, not positive. So You have to be just, yeah, go ahead.
There's some loss in our capacitor kind of when we switch to the other side.
Yeah, I mean, here we are assuming every component is ideal. So really there's no loss. Yeah. But in real life, of course, there's resistance of the inside the diodes, and there's also some sort of, time to charge the capacitors. So it's not going to be perfect waveform. But of course, you can always, again, after this, you can use a super diode so that you don't care. Okay, they're almost ideal, right? So it really works very nicely when you have all this. So I know that we're going to have some time, so I have some slides that I want to together with you guys to do some sort of very quick, recap on what to do with kind of diodes. So these are very simple circuits, but all kinds. So yeah, so look at A. Is a D1 going to conduct?
D is positive.
Yeah, if Vi is positive, there's going to be current flowing through 1K. If Vi is negative, no current. Right? So this is kind of a half-wave rectifier that you saw before. And the output will, depending on what type of diodes we are assuming. If we assume ideal diode, it's going to be same as Vi. If you assume the constant voltage drop, it's going to be minus 0.7, right? So, okay. So how about the B?
That it is, the VI is negative, and depending on our diode, we will have a 1.4 volt drop.
Yeah, right. Oh, yeah, depends on whether it's ideal, whether it's voltage drop. So if it's Vi is negative, there is output. But if Vi is positive, no output. But if the ideal diodes, Vi is negative, we will same as Vi, and so on. So current flows up. Current flows up.
And also assuming we have no breakdown.
Yeah, of course. So current can flow this way. Current can flow this way. How about C?
Oh, without breakdown.
With all two diodes back to back, there's going to be no current. Okay, how about D?
Always be full of D. It's similar to A.
So this is very interesting. Let's say D1 and D2 both are real diodes, and you would have VO equal to Vi. When Vi is positive, but when D1 and D2 has a voltage drop of 0.7 volts. And one of the previous homework and student was interesting. They said, well, D1 and D2 are in parallel, each of them is 0.7, so they're in parallel, so the voltage is going to be 0.35 because they're in parallel. I mean, they're going to divide the voltage by 2.
No, not resistors.
Not resistors, voltages, yeah.
Voltage in parallel is the same.
The voltage is in parallel, so the voltage is the same. You don't change it to
The
0.35.
this way is that we can avoid breakdown because now we have the current.
Oh, breakdown is when negative voltage is too high.
Yeah.
It breaks down the pin junction. Current can flow backwards. That's called breakdown.
Well, also that line point where our current,
You mean forward?
the forward, yeah.
Yeah, forward direction we don't call it breakdown.
What is it? Which is forward?
It's just the current continue to increase. You increase your current capability. If let's say one diode can conduct 5 milliamps, now it can conduct 10. There's 2 of them. If you exceed 10, what happens? It's not breakdown, it's actually burning up.
Well, yeah, but it also protects from breakdown because now.
No, it doesn't.
current-
It doesn't protect breakdown because you have 2 in parallel. If it,
Well, isn't the current, wouldn't the backwards current be split
well,
between the two?
well, the diode breakdown means it's breaking down. So it's the voltage. It's the voltage. It's not the current. So when you reach a certain voltage, they will both break down. You only dividing current by half each, right? It's slower in burning up.
Okay.
Yeah, but it doesn't.
Can
You could.
diodes mathematically to like help in some way, or does it just doesn't help us to combine diodes?
Yeah, you combine. We do combine. We do them in parallel to increase current capability. We do them in series to increase the reverse biasing. Yeah, you do.
And you just add them?
You just add them. Yeah. All right, so let's move on. E, what happened to E?
The diode, depending if it's an ideal or not, we can just treat it like the wire.
So the diode apparently, one of them, okay, I actually just write off, I got it wrong. So current can flow in both direction. So really, this current, this diode here doesn't do anything other than this is the problem. If it's ideal diode, the output is exact same as input. But if it's non-ideal, of course,
well, you'll have like a minus.
minus 0.7, yeah. So what you can do is that with this type of circuit, you can do this sort of, if it's too small, okay, no output. Less than 0.7, between minus and positive 0.7, there's no output. Okay, and it's above 0.7, you have output, but less 0.7. If less than negative 0.7, yeah, you have output as well. Okay, so that's what we have. How about this one here? This is the same as A. The same as A, but we added this. But then you do get 2 voltage drops. When this is conducting, the top one conducting, the bottom one cannot conduct, right? So if you have a negative voltage, it's not going to happen. So only one current direction. Let's mark it the current direction just to sure. All right, and then we have G. G is interesting. It's like a exchange the components D and 1K ohm resistor between the two. Eh? So when Vi is positive and negative, what do you see? So when Vi is positive, you have current. When Vi is negative, what happens?
You don't have
the current cannot flow. So Vi is same as VO is same as Vi. But when it's positive, how much VO?
If it's an ideal diode 0, it's not.
Yeah, it's 0.7, right? So yeah, so when it's positive, 0.7. When it's negative, it's the same as Vi. So so in all these examples, let's assume, well, we can do both. Okay. Yeah, well, let's just leave it there, and we can always come back. And then for H, so for H, what happens? You can have current going down. You can also have current going up, which means the output is always something. If those, if those diodes are ideal, this output is always 0. But if diodes are not ideal, you also have output between negative 0.7 and 0.7. And this one here, I. So if you have positive, no current. But if you have negative, current can go this way. So this one says when it's positive, output is same as input. When it's negative, the output is, yeah, kind of half minus D1 voltage drop. Okay, okay, and J. When it's positive, can flow this way. When it's negative, flow at the bottom. So this actually exactly, when it's negative, output exactly half. When it's positive, output is input minus the diode drop. And finally, we have this picture here. So if it says 1 milliamps, so both diodes can conduct. Both diodes can conduct. So they're in parallel. So the current in each diode is going to be half. Yeah. And then the 2 kilo ohms across 1 milliamp, and VO is going to be like 2 plus something. Okay, so now let's assume. I guess we do one more step. Just go back to assume VD is 0.7. Now we're gonna mark up 2 values. Vi is 5, Okay, so we're gonna do two rules, VI1, VI2. So how much is VO here? If VI is 5 volts,
4.3.
and here,
It is a negative.
are you sure?
That's just a wire.
Yeah, 0, okay. And next one, if VI is 5 volts, output is 0. And if VI is negative 5 volts,
3.6.
Yeah, 3.3.
negative, how much?
3.6.
3.6, okay. Great. And here, VO is gonna be 0, 0, okay? And this one here, VO is gonna be,
It's gonna be the same as the first one. So it's gonna be 4 point.
it's gonna be same as 4.1, yeah, okay. Negative 0 volts, great. Okay, same thing here. We're gonna say VI1 is 5 volts, VI2 is gonna be minus 5 volts. So this one here, we have conducting and non-conducting. So this VO is gonna be positive, it's gonna be negative 3 volts, okay? And this one here, VO positive, when it's positive, it's gonna,
Be 3.6.
when it's negative, right, so there's no current, okay? And this one here, when it's positive, when it's negative, okay? And down here, same thing, we're gonna do VI1, 5 volts, VI2, equal to minus 5. Okay, so how much is this one here when it's positive?
0.7 volts.
0.7 volts when it's negative. And here, we have when it's positive,
Yeah, it's gonna be 5 volts.
when it's negative,
It's going to be.
Why would it be 5 if it limits, if the resistor limits are?
Well, no, it would be 4.3 divided by 2,
it'd be 4.3 by 2, right, yeah.
which equals like
Mine,
0.15 volts. Negative 2.5 volts.
okay. And then last one here, or not last one, but this one is gonna be, when it's positive,
2.815.
when it's positive. Yeah, when it's negative,
So it'd be,
2.5 volts. And the last one,
just you just divide it by half, right? So
Well, we have so this one we have to do a little more circuit analysis.
right. So it's 1 milliamp through the 2K, give you 2 volts.
Let's assume that they're
2.3.
1 milliamps times 2K, and then plus the voltage drop on the V diode, right? So that gives you 2.7 volts. Okay,
2 split 2. But it would be 1 volt.
Well,
1
isn't
volt.
it affected by the voltage of our current? Because we have a current voltage. We have a voltage in at that bottom next to the ground.
oh, you're right. Okay, I didn't see this. I thought this is a ground. No, you're absolutely right. Okay, thank you for reminding. I thought that was a ground. Okay, so that way, it's gonna be different. Okay,
That's gonna require a little more.
it's
analysis.
yeah, it's gonna do a little bit of VI. If VI is positive, and then it's gonna be different. Yeah, if VI is positive 5 volts, there's no current. So your voltage is gonna be 2 plus 2 times 1 plus 0.7, that is correct, 2.7 volts. But when VI is negative, the whole thing is going to change. So, yeah. So when it's negative, it goes this way. So this is going to be, VO is going to be VI plus 0.7 and then plus 2 times 1. So if VI is 5 plus 0.7 plus 2, that gives you minus 2.3 volts. Okay. So if VI is negative, apparently you see current goes through here. So there's 0.7 drop, right? So 5 plus 0.7 gives you the voltage of 4.3. 4.3 and plus 2 volts. So it's minus 2.3. Yeah. So we got everything correct.
So we're saying that just split every diode problem into two cases, treat one as a Y, treat one as a 7-volt drop. Or it'd be a 7-volt drop, the other one no current, and then just find whatever values we need to find just with
Yeah. Yeah. So diodes, okay, I think, let me see what time we have. We're almost there. Do you guys have any other questions? Our exam is next week on Tuesday, and it's the same time. You guys should come a little early because we're going to have you sign the attendance sheet. It's going to take time. And if you come early, everybody comes early, and then you guys can start on time. Okay? Yeah.
If we have like class 15 minutes before, is 15 minutes before
Huh?
early, and is 15 minutes before the class started going to be early enough?
Oh no, I don't mean that early. I mean just a few minutes early.
Okay.
Just the exam actually is going to open at okay. Let me answer that question. Exam is open notes, right? You can use it, but the only thing you guys cannot use during exam. We'll have 2 tiers working around, so you cannot do internet searches. You cannot do phone calls, messages, all that stuff. You can use your graphical calculator. You can use a tablet for your notes. You can use you can access your book, that, but you cannot do internet search. You cannot ask ChatGPT to help you or things like internet access. So the actual exam is going to open like 5 minutes before the class start. And if you come early, you got to sign on and you be able to start. And it closes just 2 minutes like after the class end time. So just a few reminders that you need to do all 5 problems. You don't have to, okay, but it's better to do all 5 problems. That then we'll keep all the 4 highest grades for you.
Can you explain you can take it twice, right? You can redo a problem.
For each problem, you can do it twice, or each separately, like each. Yeah, we will take average of the 2. So you have to decide if you want to do it or not.
Is there gonna be? I know that we have to bring our laptops or device to take the.
Yeah.
Are there gonna be any place? Just come with it charged, or is there gonna be any place to charge it?
To charge your laptop? I don't know. Make sure your laptop is charged.
Bring your coal generator.
I sorry about that, but I don't have a way to for me to get that.
Breaking my generator.
There is an outlet on it.
Yeah, but there are some outlets, in a classroom, but not many. And there is so there's access code, so which means the code will be given to you on the screen when the time is there. So without the code, you cannot access. And also you need a signature. So make sure you sign it. So if you don't sign it, we don't know you are here. Because of our experience in the past, have been some students here saw the words, just quickly text me without me being able to notice, text their friends somewhere. Because what I counted like 55 students in the classroom, but I got a 57 grades. So apparently 2 of them was not in the classroom. I don't know how they got to take the exam because they will never know the code because if they're not here, right? They have to get a code from somebody here. So that's why we need the signature. So you cannot tell me saying, oh, I was in the class, I forgot to sign because there's no way for me to verify. There's so many faces. I'm sorry, I just cannot remember everybody's face. I remember some of you already, but I cannot remember everybody, right? So make sure you sign it. Make sure you do all the problems. You feel you didn't do well, you can do it the second time on each problem. If you're really good, have you done the homework? I reviewed the homework solutions and read your textbook. You should be able to get that done by, say, 45 to 50 minutes. For many of you, I believe you've done that. You'll be able to do that.
Full choice.
They are all multiple choices, yeah. There's no written. So you can, yeah, by the way, have some blank paper so that you can write on to derive the solutions, right? And you just simply input the solutions. And if you have struggle, 1 hour, 15 minutes should be sufficient for, I would say, 80% of the class.
And we're not doing anything after the exam, so once we're done with the exam.
Once you're done, you can go, yeah.
Are you allowed to let us know like how many are off there, how many are diode?
It's about a half and a half. It's about a half and a half, yeah. Okay. Yeah,
2.5 problems on off ramps, 2.5 problems.
maybe slightly more on op-amp. I don't remember exactly.
Yeah.
So if it's about half and half, there's going to be more on diodes or scenes, or we could have an op-amp question that includes a diode.
You're smart. Okay, any other questions before the exam? There are 5 problems. Each problem has about 4 to 5 questions. So total around 20, between 20 and 25. So each one was like 1 point. Some of them was 2 points. Yeah.
Study resource is the homework?
Study resource? Yeah, homeworks. Yeah. Examples in the book, video examples, real examples. Yeah, do all those. Okay. Yeah. You can have iPad, but again, cannot do searches.
Just don't.
Yeah.
Just
If we find anybody searches, we're going to disqualify you. Yeah.
Wait, so we have access to the canvas, or is it just?
Yeah, you have to do it on Canvas.
You have to do it on
No,
Canvas.
I know it's on the exam is on Canvas, but can we access Canvas, like the resources from Canvas, like
The slide
lecture slides
notes.
stuff?
Those are okay.
Oh,
Yeah, Canvas is okay. Yeah. But apparently no browse type of search. Yeah.
The book, the one on like the day one already?
Yeah, book is okay. Yeah.
Okay.
Okay. But what I suggest you guys is don't rely on the book. You should need to write down your notes. Because that's way help you memorize, help you to get familiar, and also easy for you to get information. I saw students flipping the book. I don't know, many people don't have the hard copy anymore, but I said, where is it? Cannot find it. Write it down so you can find it yourself easily. Yeah. Okay. So after exam, we're going to move on to chapter 5, MOSFETs. Will be 6 lectures on MOSFETs and 5 lectures on BJT. Then we're going to have another exam on those 2 chapters.
Okay. Is the final cumulative or?
Oh, final is chapter 7 only.
Okay.
Final, we have about 9 lectures on chapter 7. Okay. Great. Well, good luck, guys. I think if you do your work, you should be able to do well. If everybody gets an A, I'm happy. I don't mind. Okay. Yeah.
How is the difficulty of the test gonna be? Is the difficulty of the test more similar to like the lecture slides or the homework? Because they both have like different.
Yeah, both, I would say.
Both.
Both, yeah.
So it could be some basically.
Yeah, that's a mix of both. Yeah.
Okay.
Yeah.
Thank you.
Uh-huh.
Is a driver's license okay for an ID or?
Yeah, driver license okay, student ID, they're okay. They're both okay. Yeah.